Hello everyone, welcome to the clip 3 of part 8 in this wireless modern wireless communication and applications course at University of Vaasa. In this is the last clip in this course, and here we will talk about communication core of IoT. As we mentioned in the previous clip, that IoT has very important applications, and it will be like the major platform in the coming few years. It will change a lot of our daily habits, daily life, and let us see how to build, because connectivity is the major there's there's no IoT without connectivity. So connectivity, which is provided by wireless communication, is the core thing here. So let us talk today about what is the communication core available for IoT. As we mentioned before, that IoT, it has mainly four characteristics. It requires sometimes slow or medium data rate. There can be a massive number of them. Many applications, they are very time critical, so and it means that they are strict delay, and they have also very high or require very high reliability and availability. And most of the IoT applications, they are powered with limited and small energy batteries, which means that they shouldn't be consuming high energy. It is not like our mobile phone, that every time the battery that you need at least once a day, that you need to recharge it. So those IoT devices, they should work sometimes for years without replacing batteries, or at least for long time. It depends of course on the application. Yeah. So what are the communication platform suitable for IoT? In principle, that for short range, for example, it can be Zigbee, ultra wideband, Bluetooth, near field communication, or batteryless links can be used. And for large distance, we can have 5G network, which is now they have new standards in new releases that it support this ultra reliable low latency communication standard, as we will see some of them today. And also we have some new emerging technologies. They are called low power wide area technologies. Many of them, they are working in unlicensed band, these ISM bands, like LoRa and Sigfox. Actually, we have already discussed this LoRa before, but today in this clip, we are going to talk more about these technologies. Okay, and um, if we start with LoRa technology to see what is LoRa technology, we talked about it already, but let us like explain it more here. Actually, in LoRa technology, it supports star of stars technology, so it can support hundreds of thousands of IoT devices. It is very promising technology. It started in 2015, this alliance of IoT. As we mentioned before, and nowadays the alliance contains more than 500 partner or member in this alliance, and they are big companies there, or like IBM, for example, and many other companies. Now I don't remember them by heart, but I know that there are many very big, like Cisco, for example, many big companies in this alliance of LoRa. And the idea here is how to use this unlicensed band to make connectivity for very large number of IoT devices. And this can be like standalone solution. So the company can buy these IoT like devices and also the gateways and the server, and they use it for their own use or for their own application. So it is not third party based. Of course, we have some disadvantages here because it uses a licensed band. A licensed band means that we have a lot of other applications might use the same band, and in that sense, this band it might have like some security like issues and as well as high interference and so on. So one of the discussions is going around now is using cognitive radios. We talk about cognitive radios in this emerging technology that LoRa might in the future just sense if there is a free space or white space even for licensed band. Like for example 5G use some licensed band, but if 5G is not used in certain area, that band, that frequency is not used in that area, why not? Why not LoRa use that band with taking into account that will not make any like harmful interference with the 5G? So this is one option on the table. They are going on discussions about that. Might be in the future that LoRa and similar technologies will be also included as part of the 5G network, with giving also some more, let's say, freedom for the owners to control the layers there, for example, the security and so on. Okay, so in this LoRa networks, we have, as I said, stars of topology. It has three levels of devices. It is called end device ED, and this usually the sensor or actuator that communicate using the LoRa modulation. As we mentioned before, LoRa modulation is CDMA. They use CDMA with spreading factor from 7 to 12. We are not going to go into that details. Gateway is relay nodes that they collect messages from ED devices by using this LoRa interface and then forward them to the network server using reliable IP connection like IPTCP, or sometimes it can be over UDP if it is sensitive transmission, time sensitive transmission. However, that it is good to mention here, LoRa is not good yet for critical time applications because for the reason that I mentioned now, that it is not it works over unlicensed band. So it can be high interference, and the message cannot be like quite sure about the reliability of the communication. The network server is also acting the central network controller that manages the communication with the ED through the gateway. So you can see the structure of the LoRa for the IoT. So we have the end devices, and the end devices they are sending transmission to the gateways, and from the gateways can also transmit them to the network server. Um, how it works actually, it depends on the application. Sometimes the ED, when once they have data to transmit, they transmit them and then they go to sleep, so they don't wait for the acknowledgement. It depends on the application itself, and sometimes they transmit it, but they listen for some time after the transmission to hear the acknowledgement. Sometimes for the reliable connection, when the ED send transmit some packet, they want to guarantee that the packet was arrived to the network server. Once it is arrived to the network server will reply to that ED that with acknowledgement message, which means that the packet was delivered. If the packet was not delivered during that time window, the ED will send it again and again for certain number of times like 5 times, 10 times, depends on the application, till they receive the acknowledgement. How the ED is working? So actually, the ED is not, it doesn't have certain gateway, but they just broadcast the message. So every gateway listen to that message, they will forward it to the network server. So for example, if the message goes to this geteway transmit it to the network server, and this gateway also listen it, and they transfer it to the network server, and this one also the network server. Then the network server receives the same message with the same address from, like in this case, from 3 gateways. Okay, now the network server will select the best signal to noise ratio gateway that it is received to, and they will select, for example, if this one the best one, this gateway was the best one, then the network server will select this gateway to reply it is message back to the ED. Okay, so this is the selection process, but of course in the decoding process, the network server might use all of them, might use all received signals with, for example, with using like rake receiver concept. They can like combine the received signal from all gateways in order to increase or enhance the reception. But when they send back their response, they will select the best gateway or the best signal gateway to transmit it to the ED in the back channel. Okay, so this is the very like simply or very in a very basic way the operation of the LoRa for the IoT. Okay, so in ED device we have 3 classes. We have class A, class B, and class C. In class A, most of them actually use class A because in class A, most of the time the in device is in sleep mode. So they become only like awake for if they're requested or ordered by the application layer. For example, if we like measure temperature, then the sensor measuring the temperature. If the temperature becomes more than certain value, then the application layer starts to like wake the radio part of the class A of the ED to start transmit this packet to like alert or to notify the change in the temperature, or if there is fire or there is smoke or whatever. So the class A most of the time it is in sleep mode, and it becomes on only if there is a need for that. Also, these class A usually they have low data rate, and usually they have also very low duty cycle transmission. So it mean what we mean by duty cycle, it means that the percentage of time that this device is transmitting to the total time. So most actually of the LoRa application in the standard, they should support only 1% of the duty cycle. 1% of the duty cycle, it means that within 1 hour, in 1 hour we have 3,600 seconds. 1% means that within 1 hour, this ED device should be transmitting only 36 seconds, sorry. So it means that it is 1% operation, and this gives the opportunity that many sensors they can use the same unlicensed band without making like big collision and then failure of the communication link. This is in case that the sensors or the ED didn't or don't listen to the channel. In some or there are some scenario or some suggestions or proposals that don't transmit, just listen first, and if the channel is free then you transmit. It is very similar to the carrier sense multiple access with collision avoidance protocol, and in that if the sensors they equip it with that feature, then we can increase the duty cycle. It can be like 5% in sometimes. So increasing this duty cycle, of course we can use it for more applications. However, remember, by increasing this facility or this feature for listening to the channel, this also increase the power consumption inside the IoT device. So we need always to trade off and compromise between those requirements. Then we have class B. Class B actually they need to periodically send or hearing the channel. And this is the case that sensors, they are hearing all the time the action of the sensor of or if, or this IoT depends on the response from somewhere. For example, actuator. If you have a sensor connected to the actuator, and this actuator needs to take action, so every time they need to head to the channel periodically to take what action they should take. And usually this class B, they need like larger storage, battery storage, that to work for longer time. A class C, actually, they are usually like powered by main electrical grid, so we don't have any issues with the power. And for example, like smart meter connected to the utility, so in that case we don't have a problem of the power. So we have more facilities here to transmitting, to making like more processing, pre-processing at the IoT site. Okay. So there are more explanation given in those slides about the operations of the IoT. Okay, now what is the cellular network support for IoT? So now we talked about standalone support like LoRa. Now we talk about the cellular network. The need for the cellular network, as I said, because we need, in many applications we need critical time, critical mission IoT devices. In those critical mission, if the time delay is restricted by 1 millisecond or few milliseconds, and we need a reliability of 99.999%, for example, we need availability of 99.9999%, and it is in a remote area or in area that, of course, these standalone like low power wide area like LoRa or fixed application or IoT wave standard, they are not enough. They will not be suitable platforms for such critical applications. In that case, we think about cellular, or we start to talk about cellular network. In principle, most of the cellular networks can be used for some IoT applications in principle as a communication means, but because of the new requirements of the current IoT, we can see that GSM 3G and partially 4G are not suitable. If we look to the current requirements, what are the requirements? Because before, if we talk about before 15 years ago, we need like to collect data from a smart meter. So this we can use GSM modem, for example, for that application. But now when we talk about critical time applications in industry, as we mentioned, some applications, or in healthcare applications, or in traffic safety, now we talk about the massive number of devices. We talk about critical time, critical like mission applications. We talk about very high reliability and availability applications. When we look to these requirements, unfortunately, JSM 3G and most of 4G standard will not be able to provide all these requirements. Then, starting from release 12 in LTE, advanced LTE, 3GPP start to think about applications of how to support IoT applications. And then in release 12, they came with LTE Cat 0 and LTE M, where it can support IoT, and they add the possibility for sleeping mode for both saving. And then in release 13, we came with this narrowband IoT. This is one of the new technologies available, and it can operate at 200 kilohertz, which is quite close uh, to the JSM carrier band, and also close to one physical resource block in LTE band. In OFDM, we know that it is divided into each sub carrier is 15 kilohertz, and we take that every 12 subcarrier in the frequency domain, we call them as physical resource block. And this physical resource block is then 12 times 15, which means that 180 kilohertz. It is very close to this 200 kilohertz. So it is compatible between physical resource block as well as the one carrier for GSM. And then we can reuse the JSM carriers for this support of NB-IoT. Of course, it is not the same concept, but it will be still based on I of DM modulation. And with this NB-IoT, they can support very long battery life. It can be up to 10 years actually, lifetime over 5 watt-hour batteries. We have actually different operation standards for this narrowband IoT. We have standalone operation like refarmed JSM carriers, and it can be in-band operations, which will be part of the LTE carrier. So it can be like LTE in-band, as it is as this one, or it can be in the guard band operation, because when we have LTE bands, we have some guard like frequency band. We can utilize those to for that narrowband IoT. Actually, one LTE E node or next generation node base station, they can support hundreds of thousands of sensors or FIoT devices if they have very small duty cycle periods. And this is the standalone case that we can also take parts of these JSM carriers to be used with the IoT devices. What is the cloud computing and storage? Actually, the idea of the cloud is very simple because of the high reliability, very high data rate, very low latency communication, wireless communication networking that we have nowadays. Then there is no need to make all computation or storage locally in your computer or on your mobile phone. You can just transmit your data or what you need over the wireless network, and then there are servers connected to that network in the internet network where you can process your data, you can store your data there. It is called cloud computing and storage. So I give you somebody simple example. If you use your mobile phone, for example, to make some machine learning application, or for example, you want to make a processing for some pictures, and it is very high picture or very high video, for example 8K video signal with like 30-minute length, and you want to make a lot of editing in that video. If you want to do that on your mobile phone, maybe it will take many hours to do that over the processor of the mobile phone. But now, because of the very fast communication link, you can just upload your video to the over the cloud, over your 5G network. It will take a few minutes to be uploaded to the cloud. It go to the some like very high computational power server. They will make all these operations for you on that cloud, and then send you the results back. So this can be done within few minutes instead of many hours on your computer or on your mobile phone. So a lot of applications, for example, voice recognition, for simple and basic mobile phones with low computational power processors, they cannot do even simple voice recognition on their processor. It can take time. They can do that, but for example, if you want to make voice recognition for translation, and it can take half an hour on your mobile phone. You don't want to wait half an hour. The same process can be done with 1 second over the server. Then this can be sent to the server, done there, and you get the results, the voice, conversion that of the voice to the written text on your mobile phone. So or maybe you have like thousands of pictures, maybe you have many gigabytes of videos and pictures that instead of storing them in your mobile, then you want to store them on the cloud. So all these things are available, and now we have this distributed computation over the cloud. It can be used also for the networking. So in the 5G they support this is slicing, or also the virtualization of some functions of the 5G networks. This could be done also over cloud, so we will have less cost for by operators. The operators, they don't need to buy everything that as a hardware in their own campus. They can just like rent some of the computational power available, and then they can like run functions of the networking over the cloud. So this is very important actually for this IoT and the cloud architecture. More explanation are given on the slides about this. So developers now, they can provide their storage tools, software tools, data mining, machine learning tools, and visualization tools through the cloud. So you just rent them with small money, so you can have a lot of computational power as far as you have reliable and fast communication to the clouds. We have also the fog based architecture. This is actually very similar to the cloud, but instead of doing everything on the cloud, because this work can take a lot of time. I mean, the processing time and also the communication time, it can be, when I say a lot of time, I am talking about like a critical time application. Of course, when we talk about critical time application, then like 50 millisecond is a lot of time. This is what I mean. So how to reduce the time? If we can do some like processing locally or at the gateway, then we can reduce the time to instead of waiting the transmission or the processing to be done over the cloud servers. So when the servers or the cloud or the computation can be done inside or close to the IoT application, like at the gateway, then we call this as a fog based. And now we have also very important new application. It is called edge computing and IoT. The edge is more related to the cellular network itself. So you can see that beside the base station, we have edge server. Okay, now if you have like IoT device connected like with this narrowband IoT is connected to this node B, or next generation node B, we don't wait this to be done on the cloud computing. For the critical application, it can be done at the edge server. So beside the base station, we have, maybe inside the base station itself, we have like strong enough server that they can do a lot of operations needed by the IoT like application. Okay, so in that sense we can reduce the time. In that sense, we can have only 1 millisecond delay. For example, if we have autonomous car for the safety, traffic safety, then we don't need to take this to the up to the cloud here. It can be very long time. So now we can have the response within only 1 millisecond as a locally processing at or processed at the node B. This is called edge computing. Okay, so you can see here some like roughly delay 1 millisecond if you make this operation within the base station. If you want the delay up to the gateway, okay, to the packet gateway, it can be from 12 up to 24 millisecond. The delay that you take by sending your packet through the internet, it can be from 15 up to 150 millisecond. Let us take the smallest time. If we take the 15 and here 15, it is 30 millisecond. Okay, now if you take this your packet to the cloud, assume that the processing time at the cloud is 20 millisecond. So we have 30, we have 20 is 50, and another 30 to respond. So 30 and 30, 60, and 20 is 80 millisecond, or about 100 millisecond. In some applications, this is very large time. Okay, and because of that, also the reliability is small. the reliability when you send packet over the packet data network is small. There is a high chance that the packet will not arrive to the cloud or to the server there. Sorry, to the server connected to the internet to the internet network. Okay, so we lose reliability, we lose time. So for the very high reliable and very like responsive requirement, we need to do that with the edge computing. But what if we have several edge computing distributed over like many base stations? For example, we have big factory, distributed factory, where some of the sensors are connected to some node B and other sensors connected to other node B and so on. So how can we manage this one? Of course, in that case, if we have one aim, we can make distributed computation in this case. And also, in some situation that if the data required to be done in the edge server is very large and we have a lot of demand at that base station, and this edge server in another base station, it has much less demand for the processing, then we can have this communication between node B and another node B without going through the network, and we can have this intercommunication or intercommunication between two nodes in order to have distributed processing. This distributed processing actually is one of the current hot topics, how to handle like some tasks with the distributed servers or distributed processing. This is one of the very important application for the near futures. For the near future, we will have a lot of like research in that area. Okay. In that sense, if we go back to the previous slide, if we have some application that it can be divided into two, like a quality of service requirement, even from the same site. The autonomous car, they send data. This data is time critical, and this data is non or elastic or non-time critical, but needs a lot of power because there's a camera in the autonomous car. So we need to save for example, the traffic, to store the traffic video, or to have some processing which needs a lot of like machine learning or extraction or pattern recognition based on that. But in the same time, we have a small like ultrasonic radar in the car, and now we need some fast action. So now we have two types of data. One is time critical, one is non-time critical but high power requirement. Then this can be divided into two paths. One path is taken here in the local, in the edge server. The second path is taken to the cloud. So we can manage actually this, and this is one of the future 5G applications. So as we said, that distributing computing paradigm can be extremely important topic in the future. Okay. The question now, what is the best wireless network that you should select for your application? Or it depends on the application itself. There is no single technology or solution that it will be ideally suitable for all different potential massive IoT applications. It depends on the IoT application, depends on the market situation, depends on the spectrum regulations in certain countries, and so on. So as a result, so we can think about the available solutions, and then we select the best one for our own applications. So the best option depends on the application, available budget, coverage area, required quality of service, and so on. The final stage now. What is next? We talked in this course about modern wireless networks. We talked about the requirement, the basics of communication, digital communication, wireless channels, available technologies, emerging technologies, and the question now, what is next? Okay, it is actually a big question, but we can say that time critical communication is the foundation of a future time sensitive applications such as cloud gaming, AR, VR, XR, closed loop, fast automation systems, industrial control, and so on. So optimizing the wireless communication networks for time critical as well as high reliable applications will be the major issues for this decade. Most of future systems will be smart and autonomous. Okay, we will have smart home, smart city, smart safety, smart health. So everything will be smart field, smart society, and so on. So everything will be smart around us. Therefore, what we need also our communication network to be smart. So smart or intelligent wireless networks is needed, is the core for the next generation cellular networks, which is might be named as 6G, or it can be named anything else, but next generation of communication, and we are starting the mission now that it should be intelligent. The networking should be intelligent and smart enough to handle smart and intelligent applications. So this will be the future, and that's all about this course. And I hope that it has covered the requirements for and give um, like general picture about communication from signal, from time domain, frequency domain, analog communication, digital communication, wireless channels, um, 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 like recent and advanced modulation techniques from OFDM to CDMA, how to handle like challenges like diversity, like frequency fading, like fast fading, slow fading, all these wireless channels problems, how to handle them, like improving the spectrum, improving the spectrum efficiency, using diversity, equalization, MIMO, massive MIMO, and also technologies starting from Zigbee, Bluetooth, Wi-Fi, to the cellular network, starting from the 3G to the starting from GSM actually to the 3G to the 4G to the 5G to the emerging technologies to cognitive radios to up to now what will be next. I hope that of course we didn't go in very details about everything that we talked about, but in the same time we were not very superficial. We give the enough requirement of knowledge that is needed. Now it becomes necessary for everyone in technology or even in business, and to know these terms. Now they become unnecessary, not an optional, to know what is going on in these areas. So I hope that we did at least part of this mission, and this is the end of this course. And I would be very happy for your feedback, your suggestion, your proposals, corrections, everything is that you think it is worthy to say, welcome. Thank you very much. And so this is the last slide. Thank you. Bye.